Okay, today we will talk about the last point in this chapter on electric field and electric forces, and that is what happens if we put 2-point charges next to each other. Okay, so just a quick review. We agreed that if we put a charge somewhere in space, it will create around it an electric field. Okay, how do we draw these electric field lines? So these in red are electric field lines. Okay, so there are electric lines. Now, how do we draw them? We draw them in such a way that if Q is positive, electric field lines are outward. Okay, they are outward, so they are away from the charge, away. If Q is negative, as in the second drawing, then electric field lines are inward. Okay, inward, that is toward it, they come toward it. Now, what happens if we put 2-point charges very close to each other? Very close to each other. So these rules still apply. If Q is positive, electric field lines are outward. If Q is negative, electric field lines are inward. So let's start. We have this point charge over here, and I want to draw electric field lines. So I start away from it. It's like this. It's outward, it's outward, it's outward. And then as I come closer to the other point charge, also this one, away from the other charge, it's outward, it's outward, it's outward, it's outward, it's outward. Okay, and then I want to draw it outward, but the other charge starts repelling it, so it will be in this way. Okay, so it will be in this way, outward, outward and away from the other charge. So the same thing will happen in this direction. Okay, and the same thing will happen for the second point charge. I'm sorry the drawings are not perfect because Zoom doesn't allow me to draw very nicely, but this is how they will look like. So it's outward completely from the other side, but on the side where they are close to each other, they will make these, they will be outward and away, so they don't cross each other. The same thing happens with when we have two negative charges. The only difference is that they will be inward, 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 and then close to in the area, in the vicinity of the second charge, it will be like this. Okay, inward like this, and it will be inward like this, and inward like this. Okay. Now, what happens when we have one positive, one negative? So this is positive, so it will be outward, outward, outward. This is negative, it will be inward, inward, inward. And then in the vicinity of the second charge, it will leave from here, but the other one will attract it. Okay, it will leave from here, but the other one will attract it. So the electric field lines will be like this. Now let's look at a more proper picture. So in this case, these are positive and negative charge again. So we will have outward, 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 inward, 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 and then between them, it will leave the positive, go to the negative. It will leave the positive, go to the negative. If the two charges are positive or negative, it will look something like this. So if they are positive, it will be outward, 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 and in between, it will be like this. The same thing on the other positive charge. Now, if they are both negative, the only difference will be that instead of outward, I will have inward arrows. Okay, that's the only difference. Now, how do we draw? There are rules to how we draw these lines. So the number of field lines leaving the positive charge equals the number terminating at the negative charge. This happens if both charges are equal. So if both charges are equal, let's say this is 10 nanocoulomb, this is 10 nanocoulomb, then the number of field lines leaving the positive charge are equal to the number of field lines terminating at the negative charge. Now, what happens if they are not equal? Like in this case. So if I see a drawing like this, it means Q1 is bigger than Q2 because the number of field lines from Q1 is bigger than the number of field lines leaving the Q2. Okay, so now let's count. So here I have 1, 2, 3, 4, 5, 6, 7, 8. So the number of field lines of Q1 is 8. The number of field lines for Q2, 1, 2, 3, 4, implies that we apply this formula, Q1 over Q2 is equal N1 over N2 equal to 2. So if Q1 equal 10, implies and Q2 is equal to 5 because I will apply Q1 over Q2 equal to 2, 10 over Q2 equal to 2, so Q2 will be equal to 5. Okay, let's take another example. So this is another example, Q1 equal 20 microcoulomb. Deduce the charge of Q2. Okay, so first deduce the charge of Q2. I look at this. Q2 is here and the field lines are inward, implies what is the charge of Q2? It's negative because they are negative. So because they are inward. So Q2 is negative since the electric field lines are inward. Then we have to deduce not only the charge, we also need to find what is Q2. So we use the formula Q2 over Q1 is equal N2 over N1. Now we count. What is N2? What are the field lines of Q2? It has 2. What about Q1? It has 1, 2, 3, 4, 5, 6. So N2 is 2, N1 is 6, implies this is 0.66. And I know that Q1 is a 20 microcoulomb, so I put it in the formula, and I get Q2 is minus 13.33 microcoulomb. Okay? Solve some exercises from your booklet. Okay, the figure shows electric field lines for 2-point charges separated by a small distance. Determine the ratio of Q1. So this is part A. Determine the ratio Q1 over Q2. Okay, so this is equal to N1 over N2, where N1 is the number of field lines from Q1, N2 is the number of field lines from N2. Okay, now we come N1. How many field lines? 1, 2, 3, 4, 5, 6. So it is 6 over the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And this is 0.33. Okay, so we got the ratio. Part B, what are the signs of Q1 and Q2? I come to Q1, the electric field lines are inward. So for Q1 is negative because electric field lines are inward. What about Q2? They are outward. So Q2 is positive because electric field lines are outward. Okay. Now, part C. If Q2 is equal 12 millicoulomb, find Q1. So here we will say absolute value of Q2 divided by absolute value of Q1 is equal to N2 over N1. Okay. Or we can use, we start with Q1 over Q2. because then we can just use part A. So N1 over N2. And this is equal 0.33. Now Q1, Q2 is 12 millicoulomb. So it's 12 e to the minus 3. We divide by 1,000. This is Q2. So absolute value of a Q1. Q1 is negative. Okay. So absolute value of a Q1. So Q1 and absolute value is equal to 0.33 times absolute value of a Q2. Q2 is positive, so it is the same as a Q2, which is a 12 e to the minus 3. And this will give me 4 e to the minus 3 coulomb, or 4 millicoulomb. We can say it in coulomb. That's not a problem. Okay, but we have to pay attention. So this is Q1 implies Q1 is equal minus 4 millicoulomb, or minus 4 e to the minus 3 coulomb. Okay, because Q1 is negative. Another exercise. So here is the solution. Sketch the electric field pattern around 2-point charges of minus 11 millicoulomb and 22 millicoulomb placed next to each other. So let's put 2 charges close to each other. Okay, 2 charges close to each other. This is the Q1. It's negative. This is a Q2. It's positive. Okay, so we know that overall we will have outward, 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 then outward, but it will be attracted by the other one. So I have Q1 in absolute value divided by Q2 in absolute value, because now we need to decide what are the N1 and N2. Equal to 11 over 22, which is half. So the number of field lines leaving Q1 or entering Q1 should be half those leaving Q2. Okay, so let's say that we will draw 4 field lines here. So 4 outward. Okay, in this case, there should be only 2 inward. Okay. Now, if you count, I have 2 entering Q1 and 4 leaving Q2. So Q1 over Q2 is equal to half. 2 over 4 is equal. So check. N1 over N2 is equal to half. So this is correct. Is this the only solution? No, this is not the only solution. There can be many other ways. So let's take another 2 charges, the same Q1 and Q2. Instead of leaving 4 entering 2, we can make entering 4 leaving 8. So here we can make 1, 2, 3, 4. Okay, and then 4 entering the other one. So 1, 2, 3, 4. Okay, so this way we also have the same. We have a Q1 over Q2 is equal to half. So this is Q1 and this is Q2. Okay, so there is many solutions to this exercise. Okay, let's continue. So this is what I did. Sketch the electric field pattern around a negative point charge of minus 2 millicoulomb and a positive point charge of 0.5 millicoulomb. So similarly, I have Q1 equal minus 2 millicoulomb. Q2 is equal 0.5 millicoulomb. So Q1 an absolute value. So N1 over N2 is equal to absolute value of a Q1 divided by absolute value of a Q2. This is equal to over 0.5, and this is equal 4. Okay. So I will choose any pattern I want in such a way that there will be 4 lines leaving the Q2 4 times entering Q1. Okay, so let's take that leaving Q2. So this is here. Let's take this as positive. This is here Q2. It's positive. And this is here Q1 is negative. So let's decide on the small one. So let's say that we will draw 2 charges. Q1 is negative, Q2 is positive. Yeah. So let's say 2 are leaving Q2. So 2 are leaving. So N2 is equal to. So Q1 should have 8. Okay. So if we choose N2 equal to, implies N1 will be equal 8. So it has already 1, 2, so it needs another 6. 1, 2, 3, 4, 5, 6. Inward because it's negative. Okay. So this is it. It's just a simple exercise, simple idea. We will practice it more next week after the holidays. Tomorrow's session, I will make a review for the exam. Okay. And in the live session, we can do the assignment together. And if you have any questions, we can do them together. So that's it for today. So talk to you tomorrow.